Well, good afternoon. Thank you for joining us. This is our second run of this today. This is Mike Mazzarese. I'm a senior engineer with AST Environmental, and our topic for this webinar today is BOS 200 and its use to remediate petroleum hydrocarbon impacts. And we'll also, excuse me, touch base on LNAPL remediation as well. So I'm sure most of you are on more webinars than you have been probably in your careers, given the current state of things, and so probably used to asking questions. However, if you're not familiar, on the right-hand side there, you'll see the question mark. Click on that and type your question down below. We have a couple of my colleagues are moderating the questions, and so this should take about 35 minutes or so, and then we'll open it up for some Q&A at the end. So this is the fourth installment in our spring 2020 webinar series, again focusing on BOS 200. Previous three, Scott Nolan from RPI discussed activated carbon, did a really nice primer on activated carbon technologies. Aaron Peacock with Microvac gave a presentation on the synergies of activated carbon and bioremediation. And last week, my colleague Derek Pizarro presented on chlorinated solvent remediation using BOS 100 and CAT 100. All of those are recorded, so if you're interested in a copy, please drop me an email. My email will be at the end of the presentation. The rest of the webinars in the spring series 5 through 8 are going to do take a little deeper dive into some specific topics. First one is going to be the RDC, or the Remedial Design Characterization. We're going to touch base on that today, but we're going to that'll be the focal point, and that's really the high density soil and groundwater sampling that we use to develop our remedial strategies. 6 and 7 are going to focus on overburden and fractured bedrock respectively, and number 8 in the series is going to focus on permeable reactive barriers. And so we have links available for all of these. We have got a kind of East Coast and a West Coast launch time frame for each one of those, so please join us if you know, something you see here today interests you and you want to learn more about one of these subtopics. So they'll describe the RPI group first, and first off, RPI, the founder of the group, they're also Bob and Scott over at RPI are hosting this webinar series, so thank you to them. They're the technology developers, and they also operate what we call our project support laboratory, which is based in Golden, Colorado, which is where I'm located. And there's their website if you want to go check them out. AST Environmental, my firm, we are in charge of, we're tasked with the project assessment and design and field QC for the RPI group. And so we actually just launched a new website ourselves a few weeks ago, so astenv.com. Check that out. We've got a lot of information on the topics we're going to discuss today, as well as a lot of or a number of project summaries. Obviously won't be able to get to here today. And lastly, the third leg of the RPI group stool is our authorized installer network. And so although you know AST is an authorized installer of the RPI products, that's kind of how we got introduced into the RPI group back in 2005. We have a group of kind of vetted partner companies around the US, with one in Canada, one in Europe, and we've got others as well around the world that we that implement the strategies that we work with our consultant partners to develop. And so they've got the proper equipment and personnel to be able to do that. So here's the RPI group footprint. Most of the US, most of Canada. In Europe, the bulk of our applications have been in Scandinavia, although if you see down at the bottom, we've also done work in the UK, France, Italy, South Africa, and Puerto Rico is actually something that's was supposed to happen and got delayed for obvious reasons due to the current environment. coronavirus, and so that work will actually happen this summer once the travel restrictions are lifted. So here's a summary of the rest of the presentation. So we'll do a review of the technology, and then we'll talk about the RDC process. Again, that'll be expanded upon next week. And then we'll talk about implementation a little bit. So we'll talk about mainly direct push injections in this webinar. I'm not going to really talk about fractured bedrock much. That's got its own focus webinar on May 19th. And I will provide one case study, one project summary for a PRB. But again, we're going to have a focus webinar on that at the end of May. And we'll wrap up with some project summaries and finally some Q&A. So the trap and treat trade name is really the umbrella term for all of the technologies that RPI provides. And so that crosses petroleum hydrocarbons as well as chlorinated compounds. Chlorinated compounds were covered last week. We're going to focus again here on petroleum hydrocarbons. And so the activated carbon is kind of the core component to all of these technologies. And that's the trap and treat. We'll get to the kind of treatment part here in a minute. But the activated carbon gives us a really wide applicability range from a concentration standpoint specifically. So if you're looking at treating the distal end of a plume, where you've got mainly groundwater mass, don't have a lot of stored mass, and you're looking to integrate a PRB into your strategy, that functions the same way it would as a carbon canister on the back end of a treatment system. But we can march our way back to the source area, and everything's got limitations, and we'll kind of talk about some of those as we go through the presentation today. But if you've got the time, and time is going to be a critical piece to that, especially if you're going after reducing saturated soil mass, we can be effective. But again, it's going to be time and maybe money too. Maybe looking at multiple applications. But I want to take one small step back and just talk about carbon here for a minute. And so, there are multiple carbon technologies that are on the marketplace. Excuse me. First off, you need to make sure that the carbon you're putting in the ground is not regenerated. Regenerated carbon can have heavy metals, and so we don't want to put heavy metals obviously into our aquifers. So make sure that the company you're using is using virgin carbon. Secondly, not all carbon is equal. What I mean by that is the different types of carbon. So if you've got a coal-based carbon versus a coconut-based carbon, they have different sorption properties. And so it's not an apples to apples comparison. And lastly, the products themselves have wide variations in the amount of the actual carbon content. RPI's carbon content is the highest in the industry, and maybe 4 or 5, maybe even more times higher than some other technologies that are out there on a pound for pound basis. So when you're evaluating projects, make sure you're normalizing it for the amount of carbon that's present in the technologies that you're evaluating. And so from a geology standpoint, not very limited. So if you're looking at it from the standpoint of I've got a sand and I've got a clay and they've got equal mass in each of those scenarios, the amount of material is going to be the same because it's based off of mass. But what's going to be different is the application. So you might be varying your injection point spacing, you may be varying the injection volume per interval, the flow rates, or maybe even the downhole tooling itself. So AST, if we're in a sand site versus a clay site, we're using different injection tips, for example. When it gets to more challenging geologies, like something like glacial till or weathered bedrock, direct push may be an option. However, we also have what we call a pre-drill technique that I have one slide specific on that subtopic here later in the presentation. And then fractured bedrock, we do quite a bit of that, and that's using straddle packers to isolate fractures. And again, that's got its own focus webinar coming here in a few weeks. And then lastly, the folks at AST, myself included, we're all former consultants and have a kind of a broad experience of integrating different technologies. So whether that's using something, integrating surgical excavations or chemical oxidation, surfactants, anything that may integrate with activated carbon to be able to meet the objectives for your project from a performance as well as from a monetary standpoint. All right, so so the activated carbon is a great remedial platform. Okay, so what do I mean by that? It means that we can, obviously contaminants are going to sorb onto the activated carbon. That's the trap and treat. And then we can load up different treatment mechanisms in with that activated carbon. And those are going to depend on the different technologies, and I'll touch base on that in a minute. The activated carbon is going to function a little differently depending on where you're using it. So I mentioned the PRB scenario where you're dealing with, let's just say double-digit, triple-digit ppb concentrations of, say, benzene. And so since you're mainly dealing with an aqueous phase mass there, it's going to function the same as a carbon can, like I'd mentioned before. That's relatively easy to source areas where the mass is it's inverted, right? Most of the mass is in the sorb phase. It's not in the aqueous phase. So how do you clean up a source area using these technologies and other technologies that are similar to it by only impacting what's available? What's available is what's in groundwater, and you have to force a diffusion gradient. So if we can go out to a site, get good distribution with the product, we're going to bring the groundwater concentrations down quickly. And again, that's on the front end. That's just the carbon. That's before the bacteria had really kicked in. But you're going to start forcing the mass that is sorbed into the matrix to start to desorb. Now, the one thing that none of us can affect is what that rate is. And I mentioned that before. Of there's the time frame component. I'll show you some slides here where we've got some long-term soil data over multiple years, and that can take, so you can see, if you have to meet a soil objective, you're in for the long haul from a time perspective and a scale of years. All right, so we talk about the treatment mechanisms. The first two bullets there, the abiotic BOS 100 or the abiotic bio combo, which is CAT 100, were discussed last week, and we're going to focus today on BOS 200, which also uses bio. So BOS 200 consists of, besides activated carbon, obviously, we're adding terminal electron acceptors, nitrate and sulfate specifically. Oxygen actually gets entrained within the carbon during the mixing process. And so the initial upfront electron acceptor is going to be oxygen, but the bacteria are going to blow through that pretty quickly. And then nitrate will be used, and then ultimately sulfate. So nitrate might be consumed in the first 3 or 4 months, and then sulfate is what our long-term terminal electron acceptor is. And so from a time frame, how long is the technology going to be viable? It's going to depend on site conditions, but I would say generally it's 18 to 24 months. So nitrate and sulfate are some of the key parameters that we're looking for post injection to be able to monitor the performance and the longevity. We also add nutrients as well as a consortium of bacteria, and the bacteria are really important. Number one is BOS 200 is unique in our industry. It's the only activated carbon-based technology that is for petroleum hydrocarbons that adds bacteria, and the reason why is because that's protected by BOS 200, the patents that RPI carries. And it's also, from a technical standpoint, it's really key to the efficiency of the technology, because you're adding a healthy population that's been designed to work with what we're adding along with it, right? The nitrate and sulfate as terminal electron acceptors. You have a robust population from day one. Without adding bacteria, you're making a couple assumptions. One is that the bacteria that are in the aquifer and sorbed into the soil already that you need, and then you got to get those to populate your activated carbon, and that's going to take time. And that's where I say it's key to the efficiency, where there's going to be a lag, where I'm going to show you some data where we look at the sorption phase, upfront sorption phase versus the eventual degradation, the treatment part. When you have that lag, you're just looking at sorption on the front end, okay? And you look at the picture on the right-hand side there, that's what BOS 200 looks like. It's manufactured by Calgon Carbon. You can see that there. Comes in 50-pound bags or 1,000-pound super sacks. That's one of AST's trailers that you see in the background with the eductor and to keep the dust down, as well as a mix tank. And something that RPI has been developing for the last few years is a kind of modified BOS 200 version, and I had to have it here just term BOS 200 plus, and that's adding food grade electron donor that's typically starch with yeast extract and an additional bacterial consortium. And what that does is it's somewhat counterintuitive, I guess, because you're adding electron donor to a site where you're trying to remediate electron donors. But what you're doing is you're boosting the population even more so than when we just add the bacteria, like I had showed you above. So we're adding some highly digestible carbohydrates, the yeast extract, and then the additional bacteria. Now this was primarily initially thought of for NAPL sites, where we were going to need that additional population, but we're actually looking at it for low concentration sites too, because if you think about it, if you've got really low benzene concentrations, 5-10 parts per billion, for example, there's not a lot of electron donor available. And so adding an additional electron donor in with BOS 200 may boost the population. And that population, since the starch is not going to adsorb onto the carbon, outside of where BOS 200 is, injected, you should get a kind of radial sort of halo effect as well. All right, so from a proof of concept for the treatment standpoint, so we've got loads of bench R&D data from RPI, and I'll show you some of that here in a minute. We've also got sites where we do total mass in, total mass out. So we do our RDC, which I'll detail here in a minute. I have a handle on the total mass in the subsurface, and then we let the site take its course for the next couple of years, and then 2 years later, come and do another soil survey and look at the percent reductions. We can also look at long-term groundwater data, something like 5 years, for example. We also have sites where we've gone in and replaced monitoring wells. I'll show you some of that, where it takes out the idea of you may have some bias from activated carbon in the monitoring well. Most wells can be rehabilitated, they can be redeveloped, but if it can't, then that well can be replaced, and I'll show you some of that here in a minute. And then lastly, compound-specific isotope analysis is a technique where you're looking at C13, C12 ratios, and it's a direct line of evidence as to whether or not you're getting biodegradation versus just sorption. Sorption is not going to shift your del ratio, and the biodegradation will. So this figure that you see on the right-hand side is soil data from a site. And I'll show you, this was a NAPL site. I'll show you the NAPL gauging data here in a minute. But this was the well where we had performed a pilot test, and the 2012 data point you see in blue was our pre-pilot test sampling. So the pilot test design was based on that information. The 2015 sampling event, which is in red, was done in concert with the full-scale injection, which also targeted this area. So this area got treated twice. And then in 2017, as part of the initial close down of the site, a third sample was collected. So you can see the time frame here kind of gets back to, I mentioned this a few times. You're talking about, this is 5 years of information. Now this is also in the smear zone, so it's not in contact with water continually. So that may have elongated the process because it's not, we don't have that diffusion mechanism that I had referred to earlier. But these are the timeframes in general when you're talking about 8,000 milligrams per kilogram TVPH. To get down to 2,000, is doable. but you just need the time and maybe multiple injection events. So here's the I mentioned some bench data, and so this is a great chart. So RPI spiked in 500 milligrams per liter of gasoline at the start of the experiment. You see the concentrations there in parts per billion, which is kind of indicative of UST source area groundwater. And then we looked at the concentrations at day 3. Now those concentrations are, that's just sorption. So you see that 80 to 96% reduction. That's just sorption. The bio really hasn't kicked in yet. And then you look at the last 2 columns where the experiment was run out for 30 and 120 days, and they analyzed for what was remaining in the aqueous phase, but then also they desorbed everything off the activated carbon and did a mass balance. And so you see at 30 days, we had 28 to 50% reduction. And then at 120 days, 78 to 95% reduction. So this is a clear line of evidence that it's not just a sorption phenomenon. It's not just a sorption mechanism. There's actual treatment and considerable treatment as well. So I mentioned replacement wells a few slides ago. This is an interesting site where the wells were actually replaced twice. They were replaced initially after the injection event, and due to some, they had to change the grade of the redevelopment, and they had to abandon the wells and reinstall them again about 6 months later. So you see the solid line there, that's the injection, the solid vertical line. The dotted vertical line is when the first set of wells were replaced, and then the hashed line is when the second well was replaced. So there were some pretty high concentrations before we got going, as you can see, up to 50 plus milligrams per liter. But if you look at pre-injection numbers, we were between 5 and 10 milligrams per liter benzene. And with one injection, we're able to achieve very good reductions and be able to maintain those. And so what's really important is, for these sites is you have to have a really good handle on what the sorb mass component is. And that's really where the RDC ties in, because if you've got significant sorbed mass that's going to compete, it's going to keep continually feeding the aquifer, you may not see results like this. So this is the LNAPL graph that correlates with this soil data here. So this is the same well, 01C, and we've got our groundwater level in meters below grade on the primary. We've got our LNAPL thickness in centimeters on the secondary. And pilot test was performed in 2012. So this was that first sampling event where we had that first soil sample. And then it was several years before we got the full scale going, which was in 2015. And you can see here that the NAPL constant, the NAPL thickness did decrease post pilot test, but there were still some inflections. There were still some 10, 15 centimeter readings, and not until we went out and did the full scale event did we see those concentration or the measurements, excuse me, be not detected. Okay, and actually, so this is a 24-month scale here, post full scale, and this actually ran out for 36 months. It's not shown here until in 2018 when the site was officially closed and the wells were abandoned. And this was one of 6 wells that were on site that had NAPL pre full scale injection, and we did not have NAPL come back in any of the monitoring wells once we did the full scale work. All right, so talk about high density conceptual site models here, and this ties into the RDC that we'll cover here in a minute. So I like to say everything works in a beaker, so why do sites fail? And so number one, it's either reagent loading or distribution for most situations. Either we didn't put enough material in the right spot, or we didn't have enough material in, or it didn't go in the right spot. And so especially with source areas, the distribution of sorb mass is extremely complex, and I like to say it typically scales with the heterogeneity of the lithology. And it's usually underestimated, you know, and because we're just dealing with a very limited data set. And I still see designs that are based on groundwater alone for source areas, which is poor practice. You know, for any technology, we need to design around total mass. So the RDC is a kind of detailed investigation to really kind of just fine tune the conceptual site model, you know, fill your data gaps, optimize the remedial design. What's important is that we get samples that where we get, you know, speciated data, but also total mass. So in the hydrocarbon sense, we're talking about total petroleum hydrocarbons, whether that's gasoline range or diesel range or both. And we're taking dense soil vertical profiles. So we're looking at sampling every 1 to 2 feet vertically. You know, top of your smear zone, maybe, you know, one sample even above that, all the way down. And maybe breaking down groundwater as well. If you've got a long groundwater screen, we can break that down using some nested wells or maybe some hydropunch. And we can do this because the RPI Project Support Lab runs all of these analyses pro bono. It's not for compliance, but it's for the upfront work to be able to go through this process and really come up with a good design. But this also really helps us, you know, manage expectations, because, you know, we want to make sure that, you know, there are no silver bullets, and we want to make sure that we're managing your expectations. So if, you know, your objectives are to get from, you know, 5 ppm benzene to 5 ppb benzene, that may not be doable with, say, one injection event. It's possible. It all depends on how that, you know, what the saturated soil mass looks like. And this process was, the RDC process was recognized in the recent ITRC guidance doc. If you're interested in a link to that, please reach out. That map that you see on the right is a site that I've been involved with, where they 10 soil borings were advanced and 91 soil samples were collected in one day. It was like a long day. It was like a 12-hour day, but still, that's a lot of samples to get for just the cost of having a geoprobe and a geologist out on the site. So there's that image that I had showed you before. So each of these little spheres is a soil sample, so you get a really good idea of what the source area architecture looks like quantitatively. And we take that information and we carve up the site into different treatment areas. And so these sub areas are broken down vertically as well, again, depending on where the mass is. All right, so get a couple slides on application techniques, and then we'll jump into some project summaries. So, you know, these are generally done direct push. They're the flow rates. The flow rates are going to be highly dependent on depth below grade and geology. The more coarse the geology, the higher the flow rate, to get a higher exit velocity to make sure that we get proper distribution. The pre-drill technique is, and I'll actually just focus on that on the next slide, since I go into that in more detail there. And then bedrock is the flow rate range can be a little more variable, depending on the spacing and the design and the geology. And then lastly, soil mixing. So we do a lot of applications where there's a, you know, there's an excavation down to the smear zone, and maybe we're seeding the bottom of that excavation. So here's a site where we're at doing some pre-drill with Sonic. We'll talk about that more in a minute. Here's what our straddle packers look like. So these will be highlighted in our fractured bedrock webinar. And then here's just a trench that it was a shallow trench to intercept. This was actually intersecting chloroform that was discharging to a creek. But so this was a BOS 100 site, but you could use BOS 200 for the same application. So that pre-drill technique that I've referred to a couple times is where you get direct push refusal, but it's not fractured bedrock, so it's not going to hold a packer. So what do you do? And so we've you know, worked with some of our partner companies within RPI Group to be able to develop this technique where, you know, you've got, you know, say glacial till, weathered bedrock, historic fill, you know, you can't get through that. So we can use like sonic or augers, get down through that refusal zone, maybe even down to the total depth, backfill that with bentonite, let it sit for usually 24, 48 hours, and then re-drill it using direct push. Because of the way that we inject and the injection tips that we use, you can think of it as like a pressure washer coming out of the bottom of that injection tip, and that's going to cut right through that bentonite and get out into the native material. Again, this is really unique to RPI Group, and it can be used with really slurries only and with the injection systems that the RPI Group uses. And we did this, we've done this up to probably 35, maybe even closer to 40 sites now. And we did a site recently in South Carolina. We went down to close to 170 feet. Okay, so we'll spend a few minutes here on some project summaries. May not get through them all, and then we'll open it up for some Q&A. So if you want to start, if you haven't been sending some questions over, please feel free to start sending those over, and we'll start fielding those shortly. So this is a PRB site, but it was also a pre-drill site. So we did a pilot test in 2015, full scale later that year, and then I did an extension to the full scale in 2017. So you can see here all these well cans. These are all the pre-drill points. So these were all advanced with sonic down to bedrock, and then you can see here we're driving a geoprobe down through that bentonite. Okay, so this is located in the northeast. It's at an active rest stop, and so it's built up with about 20 feet of blast rubble and debris from putting in the interstate, and so direct push was not really an option for us, and so we had to use this pre-drill technique. The goal was to set up a PRB and limit the mass flux up into, there's a wetlands that sits up here to the north. So this was about 150 feet long. This was after the extension, about 88 injection locations on an approximate 7.5 foot spacing. And the injection interval spanned from 26 to 34 to 57 feet, depending on where bedrock was encountered. And so you can see here that we've got in blue here, this is the total BTEX in the upgradient well that's coming into the barrier. And so baseline between 500 and 1,000 ppb, it's peaked out over 2,000. And this is our down gradient monitoring well, and you can see that it's consistently stayed pretty close to detection limits. Really small inflection here, and that really corresponds to this increase in groundwater concentrations or the increased flux from this time period. But it has since come back down. And so this is 1,000 days post pilot test. And so, as with any bio barrier, there's a maintenance aspect. So we're monitoring the sulfate on the site. This site had some natural sulfate, so may not have to ever go back depending on what that concentration does, but those wells are in place in case we ever have to go back and do any supplemental TEA injections. And so this site also had a CSIA program performed, where groundwater samples were collected up and down gradient along the center line of the plume. And the isotope enrichment was seen as compared to MW204, which was the upgradient well. So it was observed for M-propylbenzene, ethylbenzene, MP-xylenes, and 1,2,4 trimethylbenzene. The isotope enrichment, however, was not observed for O-xylene. And so the enrichment indicates biodegradation is occurring within the PRB, again, except for O-xylene. And they were able to show that this biodegradation continues 80 to 100 feet down gradient from MW204, which again is the upgradient monitoring well. So I don't think I have time to go through this project summary. We're 35 minutes in. This is scheduled for 45 minutes, and I think I'd rather open it up for some Q&A. This is a little different site. This is much higher concentrations, LNAPL pipeline rupture site. This is in Michigan, and I can just show you one graph here to kind of give you a sense of, how long-term some of these highly impacted sites, how long that they can actually take. And this site's actually had 3 injection events, 2014, 16, and 18. And those are the 3 vertical lines that you see here. And this is your benzene concentration. Now this site had a lot of sorbed mass. So this looks a little bit different than the others than the other graph that I had showed you before. And it's all tied to how much sorbed mass is in the aquifer. So we see now we've got considerable degradation from our baseline concentration about 4,500 ppb, but we're out, well, 1,800 days is the last sampling event since the initial first sampling event. And this is the here are your benzene contours for this site. Here's our baseline in 2014 with the yellow area indicating NAPL. And here's where we are 5 years later. There is some NAPL observed in one well right here and right here. I'm sorry, 2 wells, here and here. But you can see that the plume has retreated more or less south of the service road. And since we did our last injection in 2018, you go back to this data, you can see our sulfate concentrations are still elevated, and so this site is going to continue to perform for some time. So I'm going to skip through that, and I'll bring in Derek and Dwayne. We can start fielding some questions.
All right. Thank you, Mike. Good afternoon or good morning, everyone, depending on where you are. This is Derek Pizarro with AST. I've also got Dwayne Guilfoyle, president of AST Environmental, on the line with us as well. I see a couple of questions trickling in. Feel free to enter some more if you want. I'll compile those and ask them of Mike and Dwayne here. And if we don't get to your question or you think of one later, send them out to us. Mike's got his contact information up there on the screen. And if we don't address one of your questions for some reason in this forum, we'll reach out to you individually. So first question, do you recommend NAPL recovery prior to injection?
Yes, absolutely. I mean, if you can recover NAPL, then that needs to be done to the extent practicable before we get out there. Now, the one caveat that I will add to that is you can, because of the energy you're putting into the subsurface during the injection process, you can actually get increased recovery rates post-injection. So I would say, you might need 1 or multiple vac events on the front end, but then after you do the injection for a month or 2 afterwards, it may not be a bad idea because you're not going to pull the BOS out since it's entrained in the formation. And so I've had clients that have used that as a strategy, and they've actually seen greater recovery post-injection.
All right. What is the shallowest you could inject BOS 200? And what do I do if I have to pre-clear to a specific depth per my client's wishes?
So I would say not always. You're looking at maybe a 5. I've seen as far as a 10-foot pre-clearance. Anytime that you pre-clear, regardless of sort of where your injection depth starts, it's below that. It's best practice to fill that up with bentonite, let it hydrate, very similar to the pre-drill technique that I had mentioned before. And so that's just going to limit any sort of surfacing coming up when you get out there. But if you are pre-clearing to say 5 feet, you'd want to give yourself a few feet, ideally probably 2 below that in the native material to give you a little bit of a buffer to try to keep that annular seal. Does that answer the question?
Well, I understood it. I think hopefully that answered it for the.
I wasn't sure if I answered all the parts, but if you don't have to pre-clear, Dwayne, what's the shallowest we've gone? Like 3 feet?
3 feet, but your grid spacing will be tightened up to where you're on about a 3-foot grid spacing in order to be able to control the injection flow. But we have executed projects that are as shallow as 3 feet.
So, if you've got considerable mass at that shallow of a depth, then, and it's, above the groundwater table, then I would recommend trying to do some surgical excavations if possible. Try to get that out because it's going to be ideally after the injection, so that the ground is not disturbed. I think that'd be ideal. But once you get below generally 10 feet below grade, your annular surfacing issues go away. You may intersect some old soil borings or something like that, but those are really going to be your surfacing conduits. But once you're below 10 feet, you usually eliminate the annular surfacing.
Yep, and just for our attendees, if you heard some of the mention of bentonite and pre-drill, some of those applications being modified for some of these shallow applications. The May 12th presentation, webinar series presentation, will cover some of those. So do tune in for that as well. Okay, a couple other questions here. Can I achieve MCLs if I'm starting with ppm level concentration?
It's possible. We've done it. It's just a function of it's tied to the soil mass. And so if you've got a site where, that's really kind of gets into the importance of the RDC having speciated and total mass information, because then we have a better sense of, whether or not that's going to be achievable. So if you've got, for example, 80% of the mass in the aqueous phase, 20% in the sorbed phase, then I'd say, yeah, that may be possible. But if it's the inverse of that, and you're talking about 20/80 aqueous to sorbed, probably not. In the time frame that BOS is going to be active. So if you're talking about a 24-month time frame, you're probably not going to desorb all that. And so I don't think that would be realistic in, say, a 2-year window. But as you've seen from some of the data that we've shown, it is achievable. It's just it may be multiple application, heavy application for a first full scale, and then maybe it come back and do some polishing work.
And I'll kind of tie back into that question with a follow-up here from one of our attendees. How does LNAPL mass not overwhelm the absorptive capacity and degradation capacity of BOS 200?
Well, I mean, LNAPL's not floating it's not floating right on the surface of groundwater. I mean, it collects in the monitoring wells, but it's tied to saturated soil mass, right? And so, yeah, initially you are going to, and you may see it on a site where you've got NAPL or suspected NAPL, you may see an initial decrease, which is again just absorption. You may see a slight rebound. Now we don't see, it's not like chemical oxidation where you might see 100% rebound. You might see a 10, 20% rebound. And what's happening there is the carbon is maxed out, right? The bio hasn't kicked in yet, which is kind of goes back to the one graph that I showed. But then as the bacteria catches up, chews down the hydrocarbons that are adsorbed into the activated carbon matrix, then the bacteria catch up, and then you see a first order curve down from that point. So in an apple situation in groundwater, you may see a little bit of a rebound. And I think that was actually shown on the one site in Michigan. After the first injection event, there was a little bit of a bump up, but then it did decrease. So if we go back here, I think this is kind of, and this was a NAPL site. So this is kind of, I guess I probably should have pulled this up and describing it, where you see this initial decrease and then this bump up, and this went back up from 1,500 almost to 3,000, but then has really decreased more or less since then. Dwayne, is there anything you want to add to that?
Yeah, just one note is that So when LNAPL is present in the formation, the carbon is only going to absorb based on the isotherm. So it's not like that the LNAPL, because it's there and present, is going to displace the water that's within the pore matrix of the carbon. Carbon will only absorb based on the isotherm. So like Mike's saying, the carbon gets filled up, but not filled up with like free LNAPL. It's just based on the mass as it's absorbed based on the isotherms. And just like Mike said, it's got to go through the degradation process to free up additional space to be able to absorb more mass.
All right. And I guess one last question here to wrap up a great presentation, Mike. Says you refer to performing TPH analysis. When do we need to perform this, and why are you collecting this? Most states are not regulated by TPH.
Well, when would be part of the RDC process, and the reason why it's important is, we've got to look at total mass. We've got, since it's activated carbon, we've got to look at the sorption isotherms that Dwayne mentioned. So we've got to run those for, usually something like, benzene's the driver. And so, maybe we're looking at benzene, but we also have to look at TPH, because we have to look at, so for example, if you're in a situation where you've got low benzene in groundwater, but you've got a ton of TEX in soil, we have to account for that TEX. That's in the sorb phase in the design. So it's kind of analogous to what you do for chemical oxidation designs, right? So when you're doing chemical oxidation design, you're looking at your target contaminants that are in groundwater, but then you're also running a total oxidant demand test. So for the same reason, you have to account for everything, not just, benzene. So we can't, obviously specifically target one analyte. And so we've got to have, a good sense of the total hydrocarbons, whether that's TPH, GRO, DRO, or both. And so a lot of the data sets that we get don't have that. And so that's something that we really emphasize, and it really, makes sense to get some samples to the RPI lab to get those analyses done.
Yeah, it really drives the overall prediction of the performance of the site, because like Mike's saying, it's not just about the speciated, compounds, it's about the total mass. And, it's, when you're looking at BOS 200, remember the whole concept, it's about the treatment. It's not so much the carbon's just a platform. So when we get the total TPH mass, then we can back into the amount of terminal electron acceptors needed to be able to support the biological process for the complete degradation. So, a lot of people ask me the question, how long is, BOS 200 going to last? Well, it'll last as long as the terminal electron acceptors are there to support the biological process, or you run out of the petroleum hydrocarbons, which is the overall goal. So even though you may achieve a specific risk-based standard, it doesn't mean that the BOS 200 just stops. I mean, you're going to continue to have degradation, of that mass for a long time, as long as the terminal electron acceptors are there to support it. Even though you may meet your cleanup standards, you're going to continue to have degradation for the long haul.
All right. Well, I do want to bring the Q&A to a close here. I see there are a few questions regarding both RDC and installation methods. Both of those will be covered in our next two webinars, numbers 5 and 6, but we will also reach out to you individually, each of you that submitted a question, get your response in the interim. But again, I do encourage everybody to see the next series, couple in our series. We got 4 more left here in the spring, and I'll turn it over to Mike.
Yeah, thanks, Derek. I just wanted to say thank you. I know your time is precious. Everyone stay safe, and hopefully we're seeing you guys in person next time we get the chance to do these. So there's my email address. There's Bob at Trap and Treat, Bob at trapandtreat.com from RPI. Feel free to reach out to either one of us with any questions, and enjoy the rest of your day. Thank you.